Good morning. Welcome, everyone. I'm Jackie Chen from Sandia National Laboratories, and I'd like to welcome you to the online forum on the societal impacts of fluid dynamics. The forum assembles an expert panel who share via this moderated Zoom question and answer setting their views on a specific research area and how it impacts society, and likewise how this helps to drive further fundamental fluids research in fluid dynamics. This year's third edition follows on successful webinars in 2023 on fluid dynamics for human health that was organized by Tim Colonius, and fluid dynamics of clean energy transition that was organized by Tim and myself last year. So just a few words regarding the format and house rules. The co-organizers of this year's webinar are Amy Shen from Okinawa Institute of Science and Technology Graduate University, Amrapali Garanik from Oregon State University, and myself. Amy will introduce this year's topic, the esteemed panelists, and will then start the moderating the first few round-robin questions to the panelists. Amrapali will then follow Amy and moderate the remaining questions. After this, we'll then open the floor up to a Q&A session with the audience for which you can ask a question either through the chat facility in Zoom or with the raised hand option if you want to ask an oral question. So with that, I'd like to turn the floor over to Amy.
Thank you, Jackie, and good morning, afternoon, and evening, everyone. I'm Amy Shen from Okinawa Institute of Science and Technology in Okinawa, Japan. So it's a great pleasure to welcome everyone to today's APS DFD webinar on fluid dynamics, global warming, and tropical cyclones. So again, thank you for joining us from across. I know many of you are from the Pacific, the Atlantic, and also beyond. So as we know, fluid mechanics is central to understanding how global warming affects tropical cyclones. And so usually it's called hurricanes in the Atlantic and typhoons in the Pacific, so in the Asian areas. So today, our panelists will bring together leading experts to discuss how multi-phase flow thermodynamics, ocean atmosphere interactions, and also large-scale circulations influence the formation and evolution of these really powerful storms. So here in Okinawa, and we face it every day, we can feel the nice warm ocean, the atmosphere, they are always in constant motion. So the same warm waters that bring coral reefs and sea breezes can also give very rise to strong typhoons. And so they always remind us on a regular basis how closely we live with the forces that shape our planet. So to understand them, we want to talk about fluid dynamics and the science that links the motion of clouds, oceans, and also air. And so we want to know that we also how storms test resilience, reshape coastlines, and drive better forecasting and how prepared we are as a society. And so our discussion today, so before we start, I just want to highlight we're going to focus on three key themes: the formation and structure of the storms, climate and variability, and also forecasting and resilience. So before we start, I want to quickly introduce our distinguished four panelists. So Dr. Susana Camargo, who is a professor of climate at the Columbia University in the US. So she's a leading expert on tropical cyclones and climate. She's also a fellow of American Geophysical Union, and also soon she will be a fellow of the American Meteorological Society. So our second panelist is Professor Pinaki Chakraborty, so my dear colleague, professor at OIS, and also our interim dean of faculty affairs. So his work connects fundamental physics with cyclone dynamics, combining theory, experiments, and also computational work. So we also have Professor Carrie Emmanuel, who is the Cecile and Ida Green Professor of Atmospheric Science at MIT. So he's a member of the National Academy of Science and also a fellow of Royal Society. So he pioneered the study of climate change and hurricanes. So many of you probably already read his book. He's the author of Divine Wind and What We Know About Climate Change. And he also has a new textbook coming out in 2026. So finally, our fourth panelist is Professor Morgan O'Neill. So she's a professor of physics at University of Toronto in Canada. She studies the fluid dynamics of severe convection, including hurricanes and supercells. She also serves as chair-elect of the APS group on the physics of climate and is very active in global science outreach. So these are our four panelists. And so without further ado, so let me get started with the first three questions. So the first question is, what is the role of fluid dynamics, including multi-phase flow, thermodynamics, ocean-atmosphere interaction, and large-scale circulation in shaping our understanding? It's very long of the relationship between tropical cyclones and the warming climate. So Pinaki, maybe we can start with you. And at the same time, let me also share my screen. So Pinaki.
Well, thank you very much. And it's truly an honor for me to be a part of this very distinguished panel. For fluid dynamicists, I feel that tropical cyclones truly contain an abundance of very rich scientific problems. For instance, you can zoom in any part of a tropical cyclone. On the left-hand side, I'm showing an image from the International Space Station of Hurricane Florence. If you zoom in any part, you'll find an abundance of very intricate fluid dynamical processes at play. And there would be very complicated interactions. And unsurprisingly, there would be many things that we don't understand about those interactions. So as fluid dynamicists, we can play a very important role in better understanding those processes. But I would also like to emphasize something that may be less obvious. And here I should mention my perspective is that of somebody who has a background in fluid dynamics, but have no formal training in meteorology. And if you look at the problem, not from a zoomed in view, but if you zoom out and behold the hurricane as a whole, at least for me, the problem looks so insanely daunting that it's hard to even think how we can understand such complexity in a way that you can, start to ask intelligent questions. And from that point of view, I feel that having insightful conceptual models is an immensely important thing to frame questions and to truly understand problems in the right context. And in that, the work by Kerry Emanuel from 1980s was truly a revolutionary game changer, where you can see in the left-hand side, there's an actual hurricane, and on the right-hand side, Kerry modeled the mature state of a hurricane as a simple Carnot engine. A Carnot engine, every fluid dynamicist knows too well. The 4 cycles of the Carnot engine. And just to give you a flavor, the insane complexity, we have seen, videos of hurricanes. Those of who have lived through hurricanes also know how insanely complicated every detail is. And Kerry derived the maximum wind speed of a hurricane using a formula that I'm quoting below. V is the maximum wind speed of a hurricane. And you can see the other thermodynamic factors that are at play. This Carnot engine is driven by moisture flux from the ocean. So how does global warming affect maximum wind speeds in a hurricane? Here you have a lucid framework to ask questions like that. How does sea surface temperature come into play?
Thank you, Pinaki. I think this might be a good segue.
Strong hurricanes can be.
Okay.
And, it says
Sorry,
my internet connection is unstable.
Yeah, the connection. Now we can hear you.
Yeah. So what I would like to emphasize is having this kind of conceptual model is truly very, very important to even understand the very first part that I started with, where you zoom in and you ask kind of a detailed question about a specific part. How do we know how does that specific part fit in the larger picture? Is it important to study that specific part? Even for things like that, having this kind of conceptual model is an extremely important part of the thing. Finally, just to make one comment, for me, again, as a perspective of somebody outside coming into the field, I'm citing a 2-page quick study from Physics Today by Carey. I cannot recommend this short paper highly enough for anybody who wants to get interested and wants to understand more about tropical cyclones. It's a superb starting point. Thanks.
Thank you, Pinaki. And I think this is a perfect segue for the second question, which will be addressed to Carrie. So let me move to, so we have kind of 2 slides prepared by Carrie. So the question for you is, what key fluid mechanics challenges remain unresolved in our understanding of tropical cyclones?
Well, thank you, Amy, and thanks for having me. Nice to be with all of you today. I just wanted to start with an interesting story about the relationship between applied physics, applied mathematics, and meteorology, which I think has some object lessons for us, which is the whole formal approach to convection called Rayleigh-Bénard convection. And there's lots and lots and lots of work, mostly in applied math, on this. And basically you have a hot plate at the bottom, a cold plate at the top, fluid in between, and it convects. We've done that in the laboratory. Lord Rayleigh did the linear stability analysis, lots of theoretical work, but there was a problem with it, is it completely diverged from the atmospheric scientists' conception of convection. In the former case, you can never get away from the fact that molecular diffusion ultimately limits the rate of convection. Whereas in the atmosphere, it was assumed from the get-go that molecular diffusion played no role. These two groups didn't talk to each other, which set the field back decades in hindsight. The difference is that the boundary, the lower boundary of the ocean land, is thermodynamically and mechanically rough. That sounds like a trivial thing, makes all the difference in the world. So I'm showing you numerical experiments here, same model, doubly periodic box, but different boundary conditions. So the lower right square is a snap, well, they're all snapshots of wind speed not very far above the surface. The lower right square is for the classical constant temperature boundary conditions. On the left panel is the lower boundary condition. On the top, it's the upper. So the lower right one is constant T at both boundaries, and you just get turbulent random convection. If you relax that to constant flux at one of the other boundaries, you get bigger structures, but you don't get anything that looks like a hurricane. By the way, this is rotating Rayleigh-Bénard convection. Now you go to the atmospheric science limit, which is very tough to do in a lab, and it's almost never done in applied math, where you state that it is mechanical wind-driven turbulence near the boundary that's the rate limiter for the flux. So the heat flux is proportional to the temperature difference multiplied by near surface wind speed. Changes the whole thing. This is beautiful work done by Martin Vélez-Pardo and Tim Cronin a few years ago. You can see the nice hurricane you get when you put in an atmospheric scientist's boundary condition. So a lot of interesting lessons wrapped up in that. And let me just finish by going to a contemporary problem, if I could have the next slide. Thank you. So everything really happens at the sea surface in a hurricane, and it's flux limited. But there's something very interesting. As you get to high winds, as you can see in the upper left photograph, happens to be of a river, the air begins to fill with spray. And the lower picture is from a sail drone, robotic sailboat driven into the center of the hurricane. And basically the whole atmosphere is filled with spray. A cartoon of the cross section through what used to be the ocean surface is on the upper right. And we do not currently understand fluxes through an emulsion that includes bubble-filled water and spray-filled air, but there is some hope. So the lower two final diagram is two-phase fluid mechanical computations that explicitly simulate spray. And that may be our only route forward to finally understanding this problem. I'll leave you with that thought. Thank you.
Thank you, Carrie. And so for the third question, so it might be also relevant. So I will start maybe with Carrie, then we can move on to Morgan. So the third question is, how can fluid dynamics help us better quantify the probabilities of extreme events? And how might those probabilities evolve with climate change?
Well, it's a huge question that's hard to answer shortly, but I will say this, that I think an intelligent application of fluid dynamics is, at least as far as I can tell, AI approaches aside, is the only really way forward. The reason is that the temptation always, and it's a good temptation, but it's difficult in this case. The first thing you want to do is look at history, like the history of extreme events, whether they be earthquakes or hurricanes or something else, and try to do something about the statistics from that. But we know that most damage and most loss of life happens in what you just called, Amy, an extreme event. And extreme events by their very nature are rare. Because they're rare, there aren't very many of them in historical databases. And so it's actually very tough to pull out of that statistics. And the statistics aren't valid if the climate's changing, because the statistics are changing. So the only way we can handle that is through an intelligent application of fluid dynamics. And Susanna and I and a bunch of other people have tried to do this by something called downscaling, because it's not yet possible to really simulate a hurricane in a global model that has to be run on climate timescales. We can barely do it for weather forecasting. So we apply fluid dynamics to the problem to generate very, very large sets of synthetically modeled tropical cyclones, where the model is based almost entirely on fluid dynamics and maybe a little bit of statistics as well. And we have been using these increasingly to understand detailed questions about how climate change influences hurricanes. But there is one thing left out of that downscaling. As the name itself implies, it's one way. So we're not yet including the feedback of these storms on the climate itself, which I happen to think might be very important. So I'll leave it at that. Thank you.
Thank you. Thank you. So Morgan, so we can start with your first slide.
Thanks, Amy. It's great to see the other panelists. This is such a pleasure to be a part of. I guess following off of Pinaki's introduction of the Carnot cycle as a conceptual model of the heat engine, which Carrie developed, I believe, the year I was born. So it's pretty mature and it works very well. I wanted to share some work that my former student Laurel Regibo-Roquette did to study the impact of a warming sea surface on the mechanical efficiency of tropical cyclones. Now, numerical simulations of tropical cyclones are very noisy. They are model dependent. Storms are, they fire off at random times depending on the chaotic nature of the noise at the beginning of simulations. And so we had to run hundreds of simulations to get a robust result of how the mechanical efficiency might change as the sea surface temperature warms. And what we found is that as you increase the energy output from the sea surface into the dry working fluid of the storm, indeed, there is more energy accessible to the storm to drive its winds. And I want to make clear a point of departure from potential intensity theory. That is a theory for the maximum attainable winds in a storm, which really just happens at the radius of maximum winds. And it's pretty silent on that particular theory is pretty silent on the strength of the overall wind field, whether you're just considering the two-dimensional wind field at the surface or indeed the wind field of the entire vortex up to the tropopause. And so we, following work that Olivier Palouis and others have done in previous years, tried to figure out what a warmer sea surface would do. And it turns out that these messy, extremely humid, but very subsaturated storms will become less mechanically efficient in a warmer climate. And that makes intuitive sense because if we expect the relative humidity to stay roughly the same, then water vapor in the atmosphere is going to increase with Clausius-Clapeyron. That's really robustly understood. And things that happen away from saturation are extremely irreversible. And that introduces a lot of entropy sources due to the presence of these phase changes and the drag that water droplets apply on the atmosphere. And so we found that the work that goes into dealing with water in all of its phases and moving it up and down is going to cost the strength of the wind field. So they'll both go up, but actually storms will get less efficient. I don't think that's meaningfully good news for society because what we really care about is the water that comes up on shore and the peak wind speeds that do damage. But this is a nice application, I think, that my student led of trying to understand the intricacies of the heat engine and the steam cycle of the tropical cyclone.
Thank you. And so do you want to say something about this slide?
Yeah, this is just a different topic, but this is something that I'm really excited about. And I thought that this is an audience that might be very interested in this open problem. Above mostly mid-latitude storms, not hurricanes, there is something called an AACP, an above anvil cirrus plume. And you can see that really nicely from Fujita's old photographs when he was flying in little Cessnas at the tropopause to the upper left, or you can see in the upper right this kind of cirrusy kind of wake that is above the massive anvil plume below. And we have found in recent work and really realistic high resolution simulations of tropical cyclones that this feature also appears in hurricanes in the rain bands, where you can get these really extreme embedded thunderstorms that can spin off tornadoes. And the reason this feature is important is because in 2018, a team of people with whom I was not involved showed that there is a very strong statistical relationship between a feature like this popping up above the top of a storm and the creation of a monster tornado or really extraordinary hail below. It had a predictive power of, like a 31 minute lead time prediction of these really, really extreme events on the ground. And so now we're finding these in hurricanes as well. And I think that this is a nice application of fluid dynamics actually having an impact at large scale or in a statistical sense. And we don't understand the mechanism. So this is an open question for all of you fluid dynamicists. Why would we see this at the top of a storm on average half an hour before a tornado drops? What's the cause? And that's something that we're working on.
Wow, that sounds very exciting.
Yeah, that's cool.
So yeah, I think maybe now I will hand the questions over to Emma Polly.
Thanks, Amy. This is a timely question for Sujaina. What are the current bottlenecks in improving forecast of storm intensity, track, and rainfall?
Hi, hello everyone. It's a pleasure to be here. So these two bottom figures are from the National Hurricane Center, very standard. Every time we go to a hurricane conference, we see them. So on the left, you see the improvements in the National Hurricane Center forecast of track, and on the right, the National Hurricane Center trends in the improvement or non-improvement of intensity. So what we have been seeing for the last decades is a remarkable improvement in the forecast of tracks. But in the last few years, you have been the shortest lead times, it has been pretty constant. And so some people have been asking if we're getting to a limit of predictability in track forecasts. Actually, last week, 2 weeks ago, I was in Japan, and Johnny Chan had a very interesting talk about that. And he shows with some idealized simulations that, especially as the hurricanes or typhoons are making landfall, you can still have some, errors due to the way we represent the land surface interaction at landfall. And if you improve that, he showed in like some more idealized simulations, if you improved how you represent land and topography, you can still improve your track forecast. So this is like one thing that, so we are not there yet. And we need to improve how we do the land interaction, topography, the boundary layer representation in the model. So maybe we can have even more improvement. And also I have seen some papers describing that, how you represent the environmental fields in terms of, the Bermuda High that could lead to and model biases on the environmental fields, and especially the pressure features can lead to still biases in the models that could lead to error in the tracks. So I think there is still room to improve. I don't think they're going to improve in the terms of track as fast as they have been in the past. But I think it's particularly impressive how now we can have longer lead times forecasts that are much similar to what we had many years ago in terms of skill. In terms of intensity, the problem is much more complicated, and that we haven't seen a lot more improvements than we had before. Can you go back? It's still the same.
Oh, okay.
Yeah, sorry. So you see that we do not have this decreasing trend. And I think part of it is we have issues that, like, for instance, happened with in Mexico associated with Hurricane Otis a couple of years ago, that you have rapid intensification happening just before landfall. And this is the worst nightmare, because then you cannot forecast that. So the rapid intensification, when we have, the hurricane changing very fast from one category to go 2 or 3 up, that's really a big problem. And I think there's still a lot of, progress that we need to have in terms of that, in terms of, the dynamics and understanding the process. I don't think we're quite there yet. Another issue is in the case of that hurricane, they pointed out the lack of observations at which feed the weather forecast models in terms of data simulation, if we don't have enough data that we know that influence our forecast. So I think that pushing for continuing to have improvements in terms of observational data and improvement in our understanding of other process like eye wall replacement, which leads to the hurricane weakening and then strengthening again, and you have to get the right timing of that, so you have the right forecast. I think that's where the effort's going to be, and we still have a lot of work that we can do in terms of understanding the concepts and the process. The last picture on this is I was actually a little surprised how we do not have a lot of papers analyzing the skill of the the forecasts in terms of rainfall of hurricanes. We have the regular forecast of rainfall per se, but tropical cyclone forecast of rainfall, I found very few papers talking about that, and this is one of them, but it's just related to one single season in the Atlantic, and basically saying that what you expect as you go to longer lead times, the skew in forecasting the rainfall is worse. But in the big cases that we had recently in terms of huge impacts of rainfall, for instance, what we had Ida in New York, which was even the remnants of the storm, or in the case of Houston, that we had a huge flooding. The forecast of National Hurricane Center were pretty good. This huge impacts that had. So I just think we need some more analysis of that. Okay, so I think there's a lot of and of course, rainfall and convection, as Carrie already said, are one of the trickiest things for us to forecast, and the models to be able to simulate that, especially now we can go for, models that do not need convection parameterization, then I hope that will be improved in the future. Thank you. The other slides from the other figure for the next question. Thank you.
Thank you. I will follow up with the next question with you again. From high resolution simulations to data-driven models to conceptual advances, what new approaches are reshaping our understanding of the cyclone dynamics?
Well, I think that we have been seeing a huge impact of AI in our forecasts, and really the community start using them routinely, and especially the Google DeepMind has become now a part of the National Hurricane Center discussions and how they're doing. So you can see here one of their forecasts for Melissa, Hurricane Melissa, which just happened for tracks, and and they did pretty well. And there were a lot of cases discussion on social media how even the rapid intensification of Melissa has been caught up by these AI models, and as well as the regular models. The National Hurricane Center start making the forecasts for the rapid intensification days before it happened, the case of Melissa. And here you have two papers, figures from two papers comparing AI models with regular models, and you see, in some cases they're doing, this as, now, sample size is much smaller. And you see, they are doing, in terms of intensity, they are doing, in some cases better than some of the standard models, but not always. And of course, as the lead time increases, then we can they are not doing as well. But what and then I'm putting my hat here as the editor of GRL, one of geophysical research letters, and I have been seeing a huge number of papers about AI, and it's like overwhelming the number of papers we're getting. What I'm not seeing yet is using these AI models to better understand tropical cyclone dynamics and tropical cyclone interaction with climate. And maybe we're going to get there soon, but at least what I'm seeing now is like, okay, I apply AI, that's what I get, and a lot of stuff in terms of forecasting improvements, stuff like that, but not yet helping using AI to understand the concepts. So I hope that's where the community is going, but at least my personal view is that we're not there yet using AI to help us understanding the concepts, that we still need to use more traditional pathways in terms of fluid dynamics, in terms of conceptual models to do this leap, because otherwise we're just dealing with black boxes still.
Thank you, Susanna. That's interesting and kind of opening more questions for us. I'll ask my last question to Pinaki. How can advances in fluid dynamics research inform resilience strategies for vulnerable regions, for example, island communities and coastal cities?
So when tropical cyclones make landfall, whether it's in an island or on a coast, obviously the violent winds cause a lot of destruction, but even more destruction is caused by water. So near the coast, storm surge is the major cause of destruction. So for instance, I think everybody is probably familiar with the images on the television, all the destruction that Hurricane Melissa recently caused all over the Caribbean. And storm surge is driven by the violent winds of the hurricane interacting with the ocean underneath. And this fundamentally is a fluid dynamics problem. As the hurricane goes further inland, as Susanna mentioned, there's a lot of rainfall that happens from a hurricane, and that can cause a lot of inland flooding. And these hurricanes are decaying, they go into a stage of hurricane remnants, they can interact with the other weather systems around, and this can be a very, very complicated interaction. And a better understanding of the fundamental processes that then transpire as rainfall would be a crucial step forward to better predict the kind of damages that are caused by landfalling hurricanes. And finally, I would like to mention one aspect which again connects back to something I said before about conceptual models. So if we ask about what is our conceptual understanding of what happens when hurricanes make landfall and then they decay, it could be argued that the conceptual framework of the decay of a strength of a hurricane is governed by or informed by what is called a spin-down model, where a hurricane is thought of a giant vortex which is rubbing against the ground underneath, and because of frictional dissipation, the hurricane is sapped of its strength. But the hurricane also carries a lot of moisture. It is that moisture that manifests as immense rainfall causing flooding. And one of the things my group has been working on are the thermodynamical effects of that moisture in terms of how it might modulate how a hurricane decays past landfall. So on the right, I'm showing a slide on the blue curve is how the sea surface temperature went up and down in a region before a hurricane made landfall. And the gray curve is the amount of time a typical hurricane took in that specific year to decay over a certain fraction of its intensity. And you can see that the decay timescales have been changing over time, and there appears to be some kind of a modulation of the climate on the decay. And to better understand these kinds of things, we need conceptual better understanding of what happens to landfalling hurricanes. It's a very open problem, and I hope people with expertise in fluid dynamics, expertise in meteorology would also get interested in this problem. Thank you.
Thank you, Pinaki. I will hand over to Amy for now.
Thank you. So maybe we can hand over to Jackie, since
Okay. Well, I'd like to thank the panelists for a very insightful discussion on these provocative questions. And I'd now like to open up the floor to the audience to chime in and ask their questions or comment on some of the discussions we've had. So as I said before, either use the chat window or the raise hand option, and they're at the bottom of your Zoom window.
Yeah, so I see there's a chat question from Amin, so actually a colleague from OIST. Amin, do you want to speak up? Just Amin? Okay, so maybe I should just read it. Jackie, can you see the question? Amin's question is to Carrie.
Okay. Let's see, I don't see it.
Oh, okay. So let me read it. So question for Carrie. The question is, I agree that such extreme events are difficult to be captured using data-driven methods, and that numerical simulations can provide valuable insights. Considering the multitude of parameters involved in these complex dynamics, which ones do you think are the most critical to account for in the numerical simulations? Thanks.
Well, thank you for that question. I think all of us who are trying to understand physics, broadly conceived, have a great desire to simplify things down as much as they possibly can be without throwing the baby away with the bathwater. And my own experience with simple models, I would say that there are three really important things you need if you're going to simulate a hurricane. And I don't mean to say that there aren't other things that influence them, but if I had to boil it down to my top three, I would say the potential intensity, which Pinaki told us about earlier. If you don't have that right, it's very hard to get the thermodynamics of the storm right. You need to have environmental wind shear, which is known to be a very important influence on the track and intensity of storms. And you need to know about the distribution of moisture in the storm itself, and especially in its environment. And when that's coupled with wind shear, that's also known to be an important influence. So I would start with those three things. And if you're talking about the response of hurricanes to climate change, those three variables are also important. But I don't mean to suggest that it's limited to just those three. Those are just my top three.
Thank you. So Jackie, do you have any?
Yeah, I have a follow-on question to that one, actually. I'm just curious with the emergence of foundation models for AI, and you read a lot about that for weather modeling, not so much yet for climate modeling and forecasting, but I was wondering, number one, are there sufficient data? There must be huge amounts of experimental data and historical data. Do those data have sufficient information about these rare events or these tails in the distributions to be able to be useful for forecasting hurricanes or typhoons in the future? And what would it take to actually do that? And is this community working closely with applied mathematicians and computer scientists to start to test out or build these foundation models? What's the thought for this community?
Well, I'll take a first crack, and maybe Susanna would like to jump in at that. Well, I think the recent successes of AI in forecasting, for example, the evolution of Hurricane Melissa, which was an extraordinary event, even among extreme events, it was an extraordinary event. It may turn out, it's a little bit debatable to have the world's highest surface wind speed in a hurricane. It was certainly, if there was anything like that in the training base for Google DeepMind, it must have been one other event or two other events. So it sort of showed that, yeah, you can get at least out to the outer extremities of what we've observed in historical storms as a training base for AI. But the second part of your question is actually more interesting, and I'm less capable of answering, which is to what extent have the people developing these AI models reached out to meteorologists? I can't imagine that they haven't. Susanna, do you know something about that by any chance?
Not really.
Yeah.
I know
Nobody's
that a
reached
lot
out
of
to you.
meteorologists have gone to private industry. I have working, yeah, but I don't know the details of that.
Right.
Yeah, it seems like, to my mind, fluid dynamics is one of the early responders to foundation models and machine learning AI. And we have these various sub-communities, but you can't really do it all by yourself. You have to really, follow, form interdisciplinary teams to make advances in this area. So I was just curious if this community has started doing that. John?
Yeah, thanks. Several of you mentioned like a continuous increase in ability to forecast and then maybe a continuous change in strength. Do any of you anticipate a fundamental change in that? This might be a change in the quality of forecasting, some significant advance. AI might have been alluded to that. Or is there some ultra super cyclone out there that could possibly happen in a more extreme climate, more extreme ocean temperatures that's around the bend, and we're waiting for the first one of those to show up? It's kind of a out there question, but I was curious if you have any thoughts. Fluid mechanics can go unstable in strange circumstances and switch modes, so I was wondering if anyone's thought about that.
Well, I'll take a crack at it first. I mean, we have done that in the context of really large paleoclimate changes, that when you model hurricanes, the thermodynamic cycle can kind of run away when you get to a certain place in the amount of thermodynamic disequilibrium which is present, and it forms something we've called a hypercane, and we've simulated them. But you need local sea surface temperatures over 50 degrees C. And so the only circumstances we know about where conceivably you could have that is after a bolide impact in the ocean or something like that, or a massive basalt outpouring in a shallow ocean. But it's all kind of fanciful at this point. But that's the only thing that I know about where you would get a kind of big transition. The only other thing I can think of is that there are multiple equilibria in Earth's climate, and at least there are in some paleo records. You can see sudden transitions. You can see them in some global models, and it's interesting to contemplate if there's a role for tropical cyclones in that.
Okay, are there other questions or comments from the audience?
I have a question. So very naive question, just being kind of a weather model user. Since in Okinawa, so during typhoon season, usually it starts from every year from June and lasts until sometime in October. But this year we haven't really encountered any big ones. But during the typhoon season, we always worry about our travel plans and also inviting guests. So I usually use so we have the Japan kind of regional weather prediction app, and also Windy. So that's a very popular app. So most of us use. But why aren't weather models always accurate in their predictions? So we see that even on a daily basis it changes. So I'm curious which ones are more accurate in comparison to others, if there's an answer.
Well, since I hear silence, I'll take, I mean, you're up against, in the end of the day, you're up against fundamental predictability limits, as Loren showed us. So that if you had a hypothetically perfect model, you're never going to have even hypothetically perfect initial conditions. And even if they're very good, small differences under some circumstances can amplify very quickly, which is why we do ensemble forecasting. All of the big models and the AI models do that to try to quantify that uncertainty. So at early lead times, a lot of the errors are because the models aren't perfect and because the initial state isn't. But as you get further and further out, it's just dominated by fundamental chaos. And one thing to be conscious of is that there's almost certainly, although it hasn't been proven precisely, a fundamental predictability limit to weather that can't be violated no matter what you do, which we think, going back again to Lorenz, is about 2 weeks, typically about 2 weeks. So there's, even in principle, you can't really forecast in detail beyond that time.
Okay, that makes sense. Thank you.
I have another question. A couple of you mentioned that doing DNS is a really powerful tool. And you mentioned, I think, at the beginning that, considering surface roughness of the ocean is important, and it has a major effect on the solution. But DNS, even at the largest scales on the largest computers, is still nowhere close to the real, our Earth. And so are all of the parameters can be non-dimensionalized so that you can scale down? Or are there some things that are not scalable and for which you just can't simulate it properly with the DNS?
Well, over land, to the extent that the things that actually constitute the surface roughness aren't changing in time very much, it's true you can't simulate today feasibly with a DNS all the way down to the scales of turbulence, which in fact limit fluxes to and from the surface. On the other hand, there is, as you hinted in your question, very, very good similarity theory dating back many decades, which has been validated, if you will, over and over again in field experiments, which lead to things like drag laws and heat exchange laws. under neutral, stable, unstable conditions, which are quite good. So if you know the boundary conditions, you use those in what you're calling your DNS. So you're still parameterizing, if you will, the smallest scale turbulence near the surface, which is a rate limiting thing, and explicitly simulating the turbulence higher up in the atmosphere. But the one that's parameterized, unlike the parameterization of cumulus convection, the parameterization of turbulence in the surface layer is very, very good. So scaling, if you will, works. Where it collapses is in a hurricane over the ocean, precisely because the surface roughness is part of the whole problem. It's dynamic, it's always changing. And there's a whole literature on this, but it hasn't received enough attention from fluid, in my opinion, from fluid dynamicists. And it's really potentially a factor limiting our current ability to forecast hurricane intensity. We don't know what these effective exchange coefficients of. It's a mess. You know, you have drops flying in the air, partially evaporating, coming back. You can call it a mess. It's also fascinating. It's a really fascinating problem. And whether similarity theory could be developed for that, I don't know. But I tried to do it, but nobody's paid any attention to that. So I assume it's off the table now. But yeah.
Thank you. Interesting. We have a question from Amin Chichu.
So can you hear me?
Yes.
Yeah.
Oh, excellent. So yeah, just a follow-up question actually regarding also the parameters in the simulation. So one important parameter, as has been mentioned already, is a sea roughness, particularly in atmospheric models, right? The second one is the mixed layer. So the problem is during hurricanes, you have a lot of wave breaking and we have currents, etc. So basically the mixed layer can also change and vary, of course, depending on the wind speed and the seastead conditions. So I would like to know overall, what do you think of this particular parameter, like the mixed layer, and how this varies in the formation of hurricanes and intensification of hurricanes?
Well, I don't want to hog the floor, but I will say that simply because I think it's a fascinating question. You really can't forecast the intensity of hurricanes above tropical storm strength without accounting for the interaction of the ocean. And it's fascinating. Traveling hurricane is very good at exciting inertial oscillations or near inertial oscillations. The shear between the mixed layer and deeper waters associated with those causes turbulence, which mixes cold water to the surface. And you only have to decrease the surface temperature on the eye wall 2 degrees, 2.5 degrees centigrade to kill the hurricane. So even a 1 degree C drop is important. And there are many, many limitations in our ability to do this. One is that in real time, we actually don't know all that much about mixed layer depths and the stratification below the mixed layer. Argo is helping, but I think this is a big deal. This Hurricane Melissa is a good example. I've just this morning got a chart showing before versus after sea surface temperatures. And it produced a whopping cold anomaly while it was intensifying. But when it was at its really high intensity, it didn't, not much. And if you look into it, it turns out that southwest of Jamaica, where this storm reached its peak, there's an undersea platform called the Pedro Bank. I don't know if any of you have heard of it. I never heard of it. It's only about 30 to 50 meters deep, the water there. And it's in a region with relatively deep ocean mixed layers climatologically. The warm water probably went right to the bottom. So there was no chance of producing upwelling of cold water. And maybe that has something to do, I don't know. I mean, I've seen this happen before, but an analysis, if anyone does it, of Melissa should turn that. So it's terribly, terribly important. And it's amazing. And we didn't start running coupled intensity models to. So maybe somebody can help me out here. I don't think it was much before about 20 years ago for hurricane forecasting.
Thank you very much.
So there are two questions from the chat box. Let me just read the first one. How important is predicting ocean surface roughness for the prediction of tropical intensities?
Does anybody else want to take that? I've been answering all the questions. Shouldn't be doing that.
Okay, we need volunteers.
Well, you have been talking about ocean roughness and stuff like that, so you should go ahead.
I would just say yes, we have to do that, and we have to predict the roughness. And there are attempts to do that. There are wave models, for example, that are run and have been coupled to hurricane forecast models. I don't know actually if that's being done routinely in the operational models today. But the sea surface, in terms of waves, is nowhere near being in equilibrium for most hurricanes. It just doesn't have time to reach equilibrium. So you really can't parameterize that easily. You have to run a model. But it may be that the spray effect I talked about in strong hurricanes completely dominates over the waves. In fact, it's a little hard to envision how you can have short surface waves in an emulsion, as of the kind I showed you a cartoon of. So I think this, yeah, that's part of the whole prediction problem. And I couldn't tell you where the models stand in respect to that, taking that into account. I just don't know.
I'll mention something about the kind of zoo of numerical models that we use to study tropical cyclones. For example, the paper that I showed from my former student regarding the heat engine model of a hurricane assumed a constant sea surface temperature for the duration of those very long runs. Both of these things are unrealistic. And one of the ways we get around that, or we justify that, is we just assume that a realistic storm would be moving. It would be translating across the sea such that it doesn't have too much time to cool down the sea surface. But if you're running a numerical model of a TC or a hurricane, without a moving grid over a realistic ocean, then any hurricane that's allowed to sit is going to just shut itself off very quickly if you allow it to interact with the mixed layer. So one of the reasons when we run these really simple models for fixing the sea surface temperature, aside from numerical ease and being able to afford the run, is just that these hurricanes get out of their own way and they leave these cold wakes. But if they stay too long, as Carrie says, you'll get a really, really cold wake and they'll just turn off.
Great. So I have a couple more questions. Maybe I can just pick one more, Jackie.
Okay.
Yeah, so looking 10 to 20 years ahead, what breakthroughs in fluid dynamics research could most transform prediction, understanding, and mitigation of extreme storms?
Can I say something quick about mitigation? I know that was one of the goals of this panel. I think that the exposure on the coastlines and on small islands is so significantly a societal and sociological problem. And I think that science has done a lot to help us understand and forecast these things. But something that, science interpreted broadly hasn't figured out is how do you evacuate a city safely such that people don't run out of gas when they are, an hour out on one of three arteries on a highway, stuck in traffic, and they run out of gas and the storm hits them, So I think that in terms of mitigation, like the social aspects of the damage that hurricanes cause are overwhelming. And it's so beyond, the purview of just fluid dynamics, although obviously this is the key and first part of understanding the harms that are coming. But there's a lot of science to be done in terms of communication and the psychology of trust and how people receive information. And I think that's just an enormous part of it. And there are no experts in that here, but really that's where a lot of the progress will lie, is just how society can handle this threat.
Yeah, I agree. Communication, it's really a key issue kind of for, going ahead. especially, you know, in a situation like the US, we have, you know, the society is so divided and lack of trust in science. I think communicating forecasts and, you know, projections will be a really key issue in the future.
Yeah, I think speaking of mitigation, I totally agree with you. I think, you know, Japan has been doing really well. So I think the communication and also, you know, always being prepared. We have periodic drills and I think urban planning is also important. So I always, so at least we learned we should have a backpack with food, with my dog food and everything, where to go, kind of uphill. So there are kind of evacuation sites and so on. So when the typhoon or, you know, tsunami hits. But in Japan, of course, we suffer from, you know, the language barrier. And I think the government, I think, you know, for the native, like a Japanese, it's very well organized, but for foreigners, they do have some special channels. And so that's kind of more specific for foreigners living in Japan.
Okay, I think we're at the top of the hour, so we probably should close.
Yes.
I'd like to thank the panelists and the organizers one more time. I think this is very informative, enlightening. And yeah, feel free to contact any of us if you have other questions. All right.
So much for having us.
Yeah, thank you.
Thank you. Thanks for
Thank
organizing.
you, everyone, for
Take
being here, being part of this discussion.
Okay.
Bye-bye.
Bye.
Bye.
Bye.